Hi, I am Indranil Ghosh, a first year PhD student in applied mathematics from Massey University, New Zealand. So, today I'm going to talk about using Python to start learning unconstrained numerical optimization algorithms. Before that, I want to thank the whole Python Columbia community for giving me this opportunity to speak at this platform. So, this is my first Python Columbia talk, and even my first Python Columbia, and I'm really happy to be with you all. So today I'm going to cover some basic concepts like a solution, minimization, maximization, then scaling, and like what are objective functions, or like what's a gradient and a Hessian of that function. Then we'll discuss some more advanced topics like some one-dimensional optimization problems, and like how to solve them using methods called Newton's method or second method, etc. And we'll also see some Python implementations. And finally, I will briefly talk about line search descent method. So it's a very important concept for solving unconstrained optimization problems. And we'll discuss we'll discuss another method called steepest descent algorithm that and also its Python implementation. And if time permits, like I will give brief overviews on Marquardt algorithm, conjugate gradient method, and quasi-Newton. So let's get started. So like first, what's numerical optimization? Before that, here f(x), let f of x, where x is a vector, be a scalar function of vector of variables x, which is a column vector, like consisting of elements x1, x2 till xn, and this x belongs to the n-dimensional Euclidean space. And numerical optimization is the method of minimizing or maximizing this function f of x, which is the objective function, and given some constraints are imposed on the vector of variables x. And this the elements xi of x of the vector x are called decision variables. Okay, and this is how an optimization problem is formulated. So this is how it is read. You first minimize f of x given x belonging to the n-dimensional Euclidean space, subject to the constraints gk of x less than equals to 0, where k runs from 1 to m, and hk of x equals to 0, where k runs from 1 to r, and m and r both are less than n. Okay, here gkx and hkx are scalar functions too, like the objective function f of x, and they are called constraint functions. So now what's a solution? A solution of f of x is a point, the point x of star, which denotes the optimum vector, okay, that solves our equation 1. So this is our equation 1, and x at like point x star, we have the optimum value of f of x. And like now, what's a global minimizer? A point x star is called a global minimizer of f if f of x star is less than equals to f of x for all possible values of x. Okay, and similarly, we can define a local minimizer. So the only difference is that you define a neighborhood in this case, which is given by n, and inside that neighborhood, f of x star, which is the local minimizer, the x star. So f of x star should be less than f of x for all values of x belonging in that neighborhood. And this is the simple pictorial representation. So like here, the contours represent the f of x, the function of the objective function of x, and the red line and the blue curve, they represent the constraints imposed on the variable x, and the white region is called the feasible region, and the gray region is called the unfeasible region. Here the optimum value of x, that is x star, should lie inside this white region. It shouldn't go outside the feasible region. Now there is another concept called scaling. So scaling of decision variables is a very important thing to keep in mind, because if that's not done, then like some optimization algorithms fails to converge and they perform very poorly. And two of the fields where this scaling mostly affects are the like computing the optimized step lengths that we'll see later, and also the numerical gradients. So one of the widely accepted like methods to scale decision variables is to like make the values, the decision variable values, dimensionless and vary them approximately between 0 and 1, like normalize them between 0 and 1. So one should always prefer numerical like optimization algorithms that are not sensitive to scaling. Okay. Now, what's a gradient vector? So for a differential objective function f of x that maps from Rn to R, like from the n-dimensional Euclidean space to one-dimensional Euclidean space. So this is the domain and this is the codomain of the objective function. The gradient vector is given by the nabla. This is the nabla operator. So nabla of f of x that maps from Rn to Rn. So like this is a column vector. The first element is given by differentiating f of x, partially differentiating f of x with respect to the first element of the like vector x, that is x1, and the last element is represented by finding out the partial differentiation of f of x with respect to the last element of x, that is x of n. And for a smooth, if f of x is smooth, the gradient vector is like always perpendicular to the contours. So this is what they look like. Okay. And similarly, the Hessian can also be represented. So it's for Hessian to exist, the objective function should be twice continuously differentiable, taking from Rn to R, and the Hessian matrix is given by the first element. This matrix, okay, the first element is given by partially differentiating f of x with respect to x1 twice, and the second element is represented by like the element 0, 1. If we start the index from 0 of the matrix, is represented by partially differentiating f of x once with respect to x1 and another time with respect to x2, and so on. Okay, and you can also represent the Hessian matrix as with the help of Jacobian of a gradient vector of f of x. So where the Jacobian matrix is given by a vector valued function f of x is the matrix of all its first order partial derivatives. Okay, so f of x is a vector valued function in contrast to our objective function, which is a scalar valued function. And so the Jacobian of f x is given by del f del x1 so on to del f del xn. So this is actually the Hessian matrix. So this will be used in Python scripting, this equation. Okay. So we'll be using our famous NumPy package and also the AutoGrad package for calculating the gradient and Jacobian. So suppose the objective function is given by this: f of x equals 2x1 x2 cube plus 3x2 square x3 plus x3 cube x1, and suppose so we define the objective function like that, and we also import autograd.numpy as AU, and from autograd we import the grad and the Jacobian. Sorry for that. We import a grad and the Jacobian classes. Okay, and we try to find out the gradient of f at this point p. Okay, so like grad of f is so given by grad function applied on the objective function f, and similarly Hessian f is given by Jacobian of grad of f by using the equation 4 that we just discussed. And like if we print the results at point p, we'll see that these are the values that we get of gradient vector and the Hessian matrix. Okay, now suppose you want to find out the directional derivative. So this is very important concept. We'll use them later. So for a real value objective function f of x given a feasible direction, that is the vector delta, the directional derivative of the objective function is given by del fx del delta. Okay, so which is actually the dot product between the gradient vector, like the gradient of the objective function and the direction delta. Okay, and keep in mind that this delta should be an unitary vector, that is the Euclidean norm of this delta should be 1. Now let us look into a simple example. Okay, so like similarly we'll define the objective function to be this, and we'll find the gradient vector at point P, and then we'll calculate the directional derivative at the direction delta. Okay, so that is 1 by root 35, comma 3 by root 35, comma 5 by root 35. And like if you find out the Euclidean norm, you will see this turns out to be 1. So P equals to np dot array 1, 2, 3. That's this column vector. Then we define delta, that is np dot array 1 by square root 35, 3 by square root 35, and 5 by square root 35. We define the objective function. Then we similarly find grad of f using the grad function, and then the directional derivative at point P is given by grad f of P dot delta. That is the dot product between the grad f and the delta, the direction. So we'll see that this is the result that will come. Then we can also define a positive definite matrix and the positive semi-definite matrix. So a real matrix M belonging to Rn square is a positive definite matrix for a real vector V belonging to Rn if this condition is fulfilled. Okay, so V transpose M of V should be greater than 0, and for positive semi-definite, for it to be positive semi-definite, for M to be positive semi-definite, it should be greater than equals to 0. And all the eigenvalues of the positive definite matrix are positive, and the eigenvalues of positive semi-definite matrix are non-negative. That is, they can be either 0 or positive. Let's test that for our matrix this as an example, and we'll see whether it's a positive definite or positive semi-definite or negative definite. So we define M. So this is the so we use np.linear.eigenvalues for getting the eigenvalues, and bring the eigenvalues, and we'll check whether all of them are greater than 0, or like all of them are greater than or equals to 0, or otherwise. We see that running this, we'll see that our M is actually positive definite. As simple as that. So we can also define convexity. So like I'll skip this. So but this is a very important concept. So for as Nocedal and Bright in their very famous book says that our optimization algorithm to be working perfectly, these are the like properties that should be followed. That it should be robust, it should be efficient, and it should be accurate. But there might be some trade-offs between speed and memory, and between speed and robustness. Now let's dive into the unconstrained optimization problem. Okay, so like an unconstrained optimization problem deals with the finding the local minimizer x star. So we should find the local minimizer x star of the objective function, and of a real valued and smooth objective function for n variables given by this, which is formulated as minimize f of x given x belongs to Rn. Note that here we don't impose any restrictions, no constraints imposed. Okay, and this is the condition that should be followed. So f of x star should be less than equals to f of x for all values of x. Okay, in a particular neighborhood, because we are finding the local minimizer. So there are some conditions to be fulfilled. So the first one is called the first order necessary condition. So this is the equation that denotes the first order necessary condition for the local minimizer to exist. Okay, that is the dot product between the gradient of f of x star and the direction delta should be 0 for all deltas not equals to 0. Okay, so this delta shouldn't be 0. So this turns out to be the gradient of f of x star sorry for that, should be 0. Okay, and there are second order necessary conditions, which consists of the first order necessary condition, that is this, and nabla f of x star should be 0, and also that the outer product of the direction delta and the Hessian matrix of Hessian matrix of f at x star should be greater than 0. That is, the Hessian matrix should be positive semi-definite. And we'll use the SciPy dot optimize package, which is used for our optimization tasks. Like we can minimize use it for minimization of multiple layered scalar objective functions, or algorithms for minimization of scalar univariate functions, and so on. There are lots of functionalities that are provided. So this is the pipeline of an algorithm for solving unconstrained optimization task. We start with the initial point x naught, and then we keep on iterating through a sequence of successive points that are generated. So x naught, x1 till x infinity. The choice of x naught either depends on the user who knows about the problem or the structure. Otherwise, you can also give the algorithm to choose x naught. Okay, and at x infinity, some termination condition should be fulfilled, which gives the minimizer x star. Okay, the so now the for generating this sequence of points, like sequence of iterates, it should be kept in mind that like one condition should be fulfilled, that is at a particular step k, f of x n plus k should be less than f of xn to choose a particular iterate. Here k should be like k can be either 1 or more than 1, and it's a integer value. Okay? And this, one of the terminating conditions that are used is that the Euclidean norm of the gradient of f at a particular point should be less than like a very small number, that is an infinitesimal tolerance epsilon. Okay, and then we will use the line search descent method to like pick a direction delta n for the nth step, and then we perform a search along that direction to generate an iterate x of n minus 1. For that, we also need to find a very like important thing that is called the step length, and we'll see what's that after this. So a direction delta n is actually selected if for the next iterate the following condition is fulfilled, that is the directional derivative should be negative. Okay. So like for finding the new point, besides the direction, you also need to find out the step length. Okay, so that's the distance beta, which is scalar value and is greater than 0, and that can be figured out by solving a one-dimensional optimization problem. So this itself is a one-dimensional optimization problem that needs to be solved. Okay, so you minimize f of x n minus 1 plus beta delta n, given beta is greater than 0. Okay, so this is the problem statement. So you start with x naught, you find out a direction given by this arrow, you find out the step length that gives the length where x1 should be plotted, and that helps us getting x1, and we continue to get x2, x3, x4 and so on till x star where the termination condition is fulfilled. Okay, so like now this is a unimodal function where if this is the like minimizer x star, at one side of the minimizer the objective function decreases monotonically, and at other side it increases monotonically with increasing x. Okay, so now the Newton's method. So this is a form of iterative process representing the Newton's method. So here x is a scalar, so x at j plus 1 from xj can be calculated using this equation. Okay, and here we see that we need both the first order derivative and the second order derivative. Okay, and the termination condition for convergence after a large number of iterations at x star is given by the absolute value of df dx at x j plus 1 should be less than this infinitesimal tolerance epsilon. Okay, this is also called the Newton's-Raphson method. So let's see the algorithm. Okay, so we define f of x, we define df dx of x, we also define d2f dx2 of x. We initialize the starting point xj close to x star and the tolerance epsilon. Okay, so then we continue the iteration until and unless the termination condition is fulfilled. So we find out f dash, that's the first order derivative, the second order derivative at xj, and then we find xj plus 1 equals xj minus f dash by f double dash. Okay, that's the new iterate, and then we check the termination condition. If it is fulfilled, we return x star and f of x star, otherwise we carry on with the new iterate, that is xj from xj plus 1. Okay, so let's see an example. So this is f of x, that is x cube plus x square minus 1. So we start with an initial experimental point that is xj set to 2.0 and the tolerance epsilon that is 10 to the power minus 6. Okay. Now this is the objective function that is the graph of the objective function, and so we use again the autograd package to find out f prime and f prime 2, that is f dash and f double dash, the first derivative and the second derivative. Then from scipy we import the optimized module, and we define a function that returns f of x, f prime of x, that is f dash x, and f double dash x at the point x. Okay. Then we use the optimized dot root scalar function, okay, to find out the value. So solution equals optimized dot root scalar. We pass the function fp. We pass the initial point. We set f prime to be true and f prime 2 to be true. Then we set the tolerance and set the method to be Newton, because we are using the Newton's method. And if we print the solution, we see that it has converged. There are 6 function calls and 6 iterations, and this is the root, okay, that we are looking for. And this is the visualization. Okay, this ends up here. Similarly, we use the second method. So here, if we see here, like we are only using the first derivative, not the second derivative, and this is also called the Quasi-Neutral method. And here we start with 2 boundary points A and B, and we carry on iterating until and unless the difference between A and B is so short, like that we stop the iteration there. Okay, so it should be less than. So this is the termination condition. So df dx at A and df dx at B should be less than 0. So this is the like here the order of convergence is given by the golden ratio number, and for the Newton's method the order of convergence is given by the quadratic convergence. Okay. So like here again we start with f of x. We only need to define the first derivative, and then we assign. So then we continue the iteration by assigning the first derivative of f of x at A and the first derivative of f of x at B, and then we check if f dash A and f dash B is less than 0. Then we find out the new updated point. Then we check the termination condition. If it is fulfilled, we return x star and f of x star, and then we check if f dash x is 0 greater than 0, we assign the value of b to a and the value of x to b. Otherwise, we assign the value of a to b and the value of x to a, and so on. Then we again use the objective function, the new objective function, and we set a as minus 1.5 and b as 1, and the tolerance is 10 to the power minus 7. Okay, so this is the graph. We use the same thing, but here the method should be set to second, and x naught, that is a, is given by minus 1.5 and x1 is given by 1, and we set f prime to be true. Note that we are not using f prime 2 because we don't need f double dash, and the tolerance has also been set, and we print the result. Here also we find that the root is very close to 0. Okay, so this is the visualization. There are other solvers available to root scalar, that is Haley, Bisect, Brent Q, Brett H, Riddler, Thomas 748, and so on. Now for the line search descent method, for the unconstrained minimization, we see that the iterative process for this vector valued vector x is given by this. Okay, so xj equals xj minus 1 plus beta j delta j, where x belongs to Rn. Here beta j is the scalar positive scalar number at the j step. That's the step length that we need to find, and this depends upon the direction delta j, and the condition for selecting our direction delta j for the next iterative is given by this, that is the directional derivative should be negative, that we discussed before, and this is the equation that needs to be this is the minimization formulation, so that needs to be solved by using an minimization technique. So this is the whole structure. So we define f of f at x, we define nabla f of x, that is the gradient of the objective function. Then we start the initial point, that is xj, and the tolerances epsilon 1, epsilon 2, and epsilon 3. We select a descent direction delta j, and then we perform one-dimensional minimization task that fetches us the step length beta j at the j step. Okay, then we assign the value xj plus beta j delta j to a new value x, that's the new updated experimental point. And then we check for various termination conditions, various combinations of terminating conditions, and if they are fulfilled, then we return x star and f of x star, otherwise we carry on with the new iterate. Okay, so now we'll see how to use the how to find out the step length beta j for the jth step. Okay, so as we said, so this is the function that this is the task that we need to optimize, and this is the condition, but we use the wolf conditions for this task. Okay, so where the wolf conditions consist of two conditions. The first one is called Armijo condition, given by the equation 32, and the curvature condition given by equation 33. So I urge you to go forward and look into this because I don't have that much time, so I'll be first from here. So we need alpha 1 and alpha 2 and the other values that we'll see. So we'll use so this scipy.optimize already provides a very good function for calculating the step length. Okay, so we'll see this. Nocedal and Wright also defines a very useful algorithm called the zoom algorithm that's used in understanding the step length finding algorithm. Okay, so please go ahead and look into this. The slides will be available. And so what we do is that for that, let's use the Himmelblaus function, which is a two-dimensional where the x is a two-dimensional vector which is a column vector consisting of two elements. Okay, so x1 and x2, and is given by this. So we start with the starting point x given by minus 2.5 and 2.8, and the descent direction delta, that is minus 2.5 and minus 1. Then we also set alpha 1 and alpha 2, and the upper bound beta max, that is 0.6. Okay, we use the step length selection algorithm that's given by equation 30, that is this. Okay, so let's see how we do that. So here we define the objective function in Python, and we find out the gradient of the objective function using the grad function, and then we use matplotlib to plot the Himmelblaus function, and this is the function. Okay, the contour representation. So there are four minimizers. So here, and here, as can be as intuition says. But let's see. So we'll use the scipy.optimize.line search function for calculating this. Okay, so here we define the start point, that is minus 2.5 and 2.8, the direction delta, alpha 1, alpha 2, beta max, and then we find the result, that is line search. We pass f equals to him, that is the Himmelblaus function that we defined, and my f prime equals to grad him, that is the gradient, and xk is the start point, pk is the delta, c1 is alpha 1, c2 is alpha 2, and a max equals to beta max. If we see that, we'll say if we use that, we'll see that this is the result that we get. Okay, and that is the we see the optimized step length for a particular iterate is 0.04, and the number of function evaluations were made 4, and the number of gradient evaluations were made 1. So the thing is, you only need to use the first element of this tuple. And now that we have got we have calculated the step length, we just need to find out the descent direction, and for that we use this simple formula that uses only the grad of f of xj minus 1. That is to get delta j, we need only the gradient of the objective function at the point previous to that. Okay, at the j minus 1th point, and so we have just assigned delta j, and we perform the one-dimensional task that we just showed, and we find out, we use the steepest descent algorithm. Okay, and we'll use the Himmelblaus function to see the result again. So this is one example where the starting iterate had been set to 1.1 and 2.2. And so this is the same type of code, and if we go forward, so this is the steepest descent function that I have used for which is the implementation of the algorithm that I just showed to you. And if we run that using correct parameter values, we see that we end up with the value 3 and 2, which is one of the minimizers, and the objective function value at that point is 0. And this is the visualization. So we have started from here and it has ended here. So this is one of the minimizers. Okay, the numerical assumption. So I won't go through conjugate gradient and Murphy. I really urge you to go forward and look into this. So this is very simple. And yeah, so last thing, I am maintaining an online resource which is a kind of book, and it's an open source kind of book. And like this is the link to that book, and this is the GitHub repository, and this is open to all. And I really ask you to come forward and please contribute to this project, and I would be really grateful. So thank you. These are the references. That's the end. Thank you for listening to me, and if you have any questions, please shoot me an email.